Good day everyone. This video presentation contains how dynamic programming works and its algorithm simulation. What is dynamic programming? Dynamic programming thrives on 4 key characteristics, which is optimal substructure, overlapping subproblems, memorization, and 2 distinct approaches, which is bottom-up and top-down approach. Problems are broken down into stages and states, with solutions calculated using a transition function and an object function. This versatile technique has wide applications, excels in adaptability, and significantly improves efficiently by storing subproblem solutions. Dynamic programming success stems for its inherent adaptability. From its early theoretical roots with Bellman's function equations to its current applications in diverse fields like bioinformatics, finance, and robotics, dynamic programming has consistently evolved to tackle complex problems with efficiency. Its dual approaches, which is top-down memorization and bottom-up tabulation, offer flexibility based on the problem's nature. Dynamic programming's adaptability shines in dynamic environments, where scenario analysis and online learning allow it to adjust to changing conditions and uncertain data. Looking ahead, hybrid approaches, parameterized dynamic programming, and incremental updates promise further adaptability and generalization. Dynamic programming's legacy is one of continuous evolution, fueled by its ability to adapt and conquer complexity. Big data and quantum computing, dynamic programming will undoubtedly remain a powerful tool, forever adapting and shaping the future of problem solving. I'm here to perform the dynamic programming simulation. We already know how Fibonacci sequence work, right? So in dynamic programming, Fibonacci sequence is a common problem because it has a recursive function. So what we're going to do is, for example, let's make a Fibonacci sequence. To get the Fibonacci sequence, you just add the first term and second term. So 0, 1, 1, 2, 3, 5, 8, and so on. And 0, 1, 2, 3, 4, 5, 6, and so on. For example, we're using this given problem. So the given problem is I want to find the end term, and we're using the dynamic programming algorithm. So what we're going to do is we have the example function, which is int live int n. If n is lesser than equal to 1, return n, and also return n minus 2 plus f n minus 1. So this is the given function. So what we're going to do is I want to find the n term using this function. So now we're going to find the n term. So f is equals to 5, which is this is the term I want to find. Based on the example function, if n is lesser than equal to 1, just write n. But as you can see, 5 is not less than equal to 1. So let's call the two function, which is Fibonacci n minus 2 plus Fibonacci n minus 1. So what we're going to do is, let's call the two function, which is 5 minus 2 is 3 and 5 minus 1 is 4. So and now it's obviously, as you can see, it's obviously 3 and 4 is not less than equal to 1. So let's call again the two function, which is n minus 2 and n minus 1. So here 3 minus 2 is 1 and 3 minus 1 is equals to 2. So f Fibonacci. Now 1, so as you can see, the n is less than equal to 1. So just put the n. There's no child node here. And this, and it's obvious na 2 is not less than equal to 1. So 2 2 minus 2, which is 0, and 1, 2 minus 1. So here we're done here. Now in this part, so it's obvious na same process gapon, which is, let's call the two function. So 4 minus 2 is equals to 2, and 4 minus 1 is equals to 3. So as you observe, it has a recursive function. So until ma-reach na to na if n is less than equal to 1. So here if 2 minus 2 is equals to 0 and 2 minus 1 is equals to 1. Now wait to in here 3 and 1 and 2 Fibonacci 2, and then 1, 2 minus 2 is equals to 0, 0 and 1, Fibonacci 1. So we're done tracing the 3. This 3 would be the This would be the tracing tree of that particular function in the example function. For finding F5, it is making 15 calls, which is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So, is there a way to lessen the time? Well, yes. What we're going to do is to test its time complexity. So, T n is equals to 2 T n minus 1 plus 1. You just only add 1. So, the big O notation to n. It will take time if we use this function, but there's a way to reduce the time. So let's go back to the recent tree we traced. As we observe, in this function, it has a characteristic of a overlapping subproblem because the path to any node will likely pass through some of the same node as the path to the other nodes. Now we reduce the time taken by this Fibonacci function by storing the result of Fibonacci function so that once it is called the, for example, Fibonacci 1, it will not be called again. Now I will show you how it can be done. Let's say I have an array here, f, so 0, same problem. I want to find this fifth term, so call function fib5 is unknown. Now call function fib3 is also unknown, and fib1, and based in our function example, if n is less than equal to 1, the value is n, which is 1. So fib1 is 1. So fib1 is 1. So this is check. Now here fib0, it's obvious that 0 is less than equal to 1. So 0, if fib0 is equals to 0, so let's put here 0, and this fib1 is, we already know that fib1 is equals to 1, so we should not call it again. Now fib2, we all know now 0, fib1 is equals to 1, and fib0 is equals to 0. So 1 plus 0 is equals to 1. So fib2 is equals to 1. As you can see, it's already given that fib1 and fib2 is, the value is 1. Now let's just add. So 1 plus 1 is equals to 2. So fib3 is equals to 2. And here The fib 0 is already called, so let's not call it again. Fib 1 and fib 2. So fib 2 is already 1. And so let's not call this either because it's already called here. Now, and here also. Now it's already given that fib 3 is equals to 2. We just only sum these two value. Now fib 4 is 1 plus 1 is equals to 3. Now fib 4 is equals to 3. So now we just only sum these two values. So 2 plus 2 is equals to 5. So fib 5 is equals to 5. As you observe, the function called is lessen. So let's observe 1, 2, 3, 4, 5, and 6. So this is the result of memoization. By storing the result of the function when the function is already called, don't call it again. We can see that the memoization reduce the time from the previous time complexity is 2 and 2 now is n. Memoization follows top-down approach based on the tree. So we start here and here to 0. Just like here, 5, 3, 4, 1, 2, and so on. And it is called a top-down approach. So that's how memoization works. Now, same problem. I will show you how tabulation method works. Tabulation follows bottom-up approach. To solve tabulation method, let's add a loop function. So this is the previous function without loop, and this is the tabulation function with loop. Now, same problem, I want to find the fib 5. So let's use this function to find the fib 5. As I've said earlier, tabulation is a bottom-up approach. So let's start in this index, which is 0. So based on the function given, f is equals to 0. So let's put 0 here, and 1 f1 is equals to 1. So let's put 1 here. Now let's execute the increments. So I plus plus from here to here. So the 2 is the I now. Now let's execute this method. If fi minus 1, so 2 minus 1 is equals to 1. So let's put 1 here. Now next, let's execute the incrementation. So 1 I plus plus. So from 2 plus 1, so 3. So 3I is equals to 3 now. So 3 minus 1 is equals to 2. So let's put 2 here. And execute the incrementation. So now I is equals to 4. 4 minus 1 is equals to 3. And here, so we will get the 5. That's how tabulation works. And that's all. This is how we write the algorithm for dynamic programming. Dynamic programming's remarkable success hinges on its inherent adaptability. This ability to handle diverse problems from bioinformatics to finance, coupled with its dual approach flexibility, top-down memorization and bottom-up tabulation, positions dynamic programming as a powerful tool for problem solving. Dynamic programming's adaptability extends beyond static problems. Its ability to analyze scenarios, learn online, and adjust strategies in real time makes it ideal for complex domains like traffic routing and financial markets. This ability is further enhanced by hybrid approaches, parameterized variation, and incremental updates, paving the way for even more powerful applications. From its theoretical roots to its ever-expanding real-world uses, dynamic programming's adaptability has been the driving force behind its journey. Dynamic programming's adaptability is not just a convenient feature, it's the cornerstone of its success and future potential. As the world of problem-solving evolves, dynamic programming will rise to the occasion, adapting and shaping the future of optimization. That's all. Thank you for watching and God bless.